All right, today we're jumping right into the middle of some serious molecular drama. We're talking breakups, new connections, the whole shebang. This is the story of the SN1 reaction.
You know, it's easy to think of chemistry as just random particles bumping into each other, but it's not random at all. There are rules, there are pathways. It's almost like every molecule is following a script. And today, we're going to take a look at one of the most important stories in that playbook.
So what is an SN1 reaction, really? At its core, it's a simple trade. One chemical group leaves and a new one takes its place. But the real secret, the thing that makes it so special, is that the hardest part of this whole process, the slowest step, involves just one single molecule deciding to go it alone.
And the biggest clue is right there in the name. You've got S for substitution, N for nucleophilic, but that one, that's the key. It stands for unimolecular. It tells you that the speed of this whole reaction depends on just one thing, our main molecule, the substrate. The other guy, the new group that's coming in, well, it just has to sit back and wait for its moment.
So how does this whole one molecule at a time thing actually play out? Well, the best way to think about it is like a little two-act play, a story with a very distinct beginning and end. First up, we have Act 1, the breakup. This is the tough part. A piece of the molecule, what we call the leaving group, just leaves. It breaks its bond and takes off. This step is slow, it takes a lot of energy, and it's the bottleneck for the whole reaction. But once that's done, we get to Act 2, the new connection. What's left behind is vulnerable, and a new group, our nucleophile, sees its chance and swoops right in to form a new bond. And this part, it happens super fast.
Now, that moment, that tiny little pause right after the breakup, but just before the new connection, that's where we meet the real star of the show. This is the key player that makes this whole SN1 reaction even possible. So, let's meet our hero, the carbocation. The moment that leaving group is gone, it takes its electrons with it. And the carbon atom it was attached to? It's left with a positive charge. This incredibly reactive, super unstable little thing is the carbocation. And honestly, it's desperate. It wants to get its electrons back to normal. And what it does next? Well, that defines the entire reaction.
But here's the thing. Not all carbocations are built the same. Their stability is absolutely everything. A tertiary carbocation, one that's connected to 3 other carbon groups, is the most stable. It's like it has a great support system helping it deal with that positive charge. A secondary one is okay, but a primary one, so unstable it basically never happens. And that is the golden rule. The SN1 reaction really only works if it can create a stable hero, a tertiary or maybe a secondary carbocation.
Okay, so just like any good drama, our molecular breakup needs the right setting. The conditions have to be absolutely perfect for the SN1 story to unfold.
So what does that perfect stage look like? Well, first, we just talked about it. You need a substrate that can form that nice, stable carbocation. Second, you need a helpful solvent. Something called a polar protic solvent, like water or alcohol, is perfect. It helps stabilize the leaving group as it departs, and it gives our carbocation a little support while it's waiting. And finally, the nucleophile. You might think it needs to be super strong, but because it shows up after all the hard work is done, its strength really isn't a huge deal. Even a weak one can finish the job.
Now, to really truly appreciate the SN1 story, it really helps to put it side by side with its sibling reaction, the SN2. When you see them together, the things that make each of them unique just become crystal clear. And the differences are huge. The SN1 is our two-step breakup, then rebound story. The SN2, it's a one-step, totally coordinated dance. The new group attacks at the exact same time the old one leaves. So the SN1 speed depends only on the substrate, which is why it loves crowded tertiary carbons that form stable carbocations. The SN2 needs a clear path for that attack, so it prefers wide-open primary carbons. But maybe the coolest difference is the stereochemistry. The SN1 carbocation is flat, so the nucleophile can attack from the top or the bottom, giving you a mix of products. But the SN2 attack always comes from the back, completely flipping the molecule's orientation, kind of like an umbrella flipping inside out in the wind. Totally different paths, totally different results.